This last exercise here is similar to the previous one. We have to use the generating functions, but it's in a way simpler because what we have to prove is that the outcome of this sum is this expression here. And for that, we all have to apply generating functions to the left-hand side and to the right-hand side and show that they are both the same, right? So let's begin with the left, right? We don't have to worry about the summations because it goes from 0 to infinity, so it's another series, this one, right? We could extend it to minus infinity, but I don't think it's going to be necessary. We won't have the complication of interchanging summations when one of the limits is related to the parameters of this function, because in this case it's not. It goes from 0 to infinity, so we can just interchange these two summations straight away. What we're going to do is to call this sum here an, right? It will depend on x, of course, right? Because x is a parameter, n is another parameter, and it can be any non-zero integer, right? But k is the summation index, so k won't appear in the final expression. So after we perform this sum, this will be an of x. I'm leaving out this x because I don't want to keep this x all the time in the expressions, right? And just focus on the summation. And we're going to introduce the generating function, the usual generating function, sum from 0 to infinity, right? It's in the whole range of n, an times z to the n. Okay, so let me do that. So f is going to be the sum from 0 to infinity, z to the n, and then I write the sum here. So it's the sum from k0 to infinity. Then I have n plus k over 2k. And here I have x squared minus 1 over 4 to the power n minus k, right? Okay. So what I'm going to do now is to interchange the two indices here, so the two summations. Then I have the sum over k from 0 to infinity. All that there is here depends on n and on k at the same time. So next write the sum on n, so to infinity, and then everything else. Plus k, 2k, and here we have x squared minus 1 over 4 and minus k z to the n, right? Now focus on this combinatorial number, right? This combinatorial number is going to be 0 if n plus k is smaller than 2k, or in other words, if n is smaller than k. So that means that all the terms from 0 to k, excluding k, are going to contribute 0 to this. So we can just change the 0 here and write k, okay, because that's what we're going to have, right? Okay? All the other terms contribute 0. So next, we're going to introduce a new variable, which is j, so that n is equal to k plus j, right? And if j runs from 0 to infinity, k runs from k to infinity, as it is here. So I just copy this, okay, and then I change the variable. This is from 0 to infinity, right? And I have to rewrite this in terms of j. So what I have here is 2k plus j, and down here I can write 2k or I can write j, as I prefer, because both are equal, right? Then I have n minus k, that is j, and finally I have n here, which is set k and set j, right? Well, set k is the first factor that does not depend on other than just k. So what we have here is the sum from k0 to infinity, then we have set to k, and now we have the sum of the rest of the term. The rest of the term has this form. It's the sum from 0 to infinity, 2k plus j over j times something which is x squared minus 1 divided by 4 times z to the power j. And the sum of this is well known, is 1 over 1 minus this, so x squared minus 1 over 4 times z to the power 2k plus 1. 2k plus 1. There you go. All right. So what do we have now here? Well, we have the sum from 0 to infinity of something that has a power k here and a power 2k plus 1 here. So I'm going to extract one factor to get rid of this plus 1. Okay. So I write this factor here. 1 minus x squared minus 1 over 4 times z. And then I write the sum from k, 0, to infinity. And I'm going to write this as a single expression. So it's z divided by 1 minus x squared minus 1 over 4 times z, everything squared. Okay, this is squared, everything to the power k. Okay, so we have z to the k up here, and down here we have this factor to the 2k plus 1. The 1 is this factor here. This is the geometric series, so the sum of this is, I just copy this factor, right? I copy this factor here. And then the rest is 1 over 1 minus this whole factor, so z over 1 minus x squared minus 1 over 4 z to the power 2. All right, now let's see, we have to simplify this a little bit. Right, we're going to multiply the numerator and the denominator by this quadratic factor here, right? So this factor is equal to this one, but this is single and this is double. So when we multiply here and divide by this, we just get one of these factors up here. So in the numerator, we will end up with this, right? Now in the denominator, we're going to have this quadratic factor here, right? So 1 minus x squared minus 1 over 4 times z squared, right? Minus z. And I can expand now this denominator, right? Let me do this here. The denominator is 1 minus x squared minus 1 over 2. Let's double this, right? Times z. So that's why 2 divided by 4 is 2. Plus x squared minus 1 over 4 squared, z squared, minus z here. All right? Okay. And then, let's see. We have the two factors multiplying z are x squared minus 1 over 2 and plus 1 here, which means this is x squared plus 1 over 2 after reduce this to a common factor. So what we have is this. Well, let me just copy the result up here. Is 1 minus x squared minus 1 over 4 times z divided by, and then here we have 1 minus x squared plus 1 over 2 times z, right? Plus x squared minus 1 over 4 squared z squared. All right. So after doing this is what we're left with, right? Okay. There are two ways to proceed now. But we're going to adopt the easy one. We're going to leave this here. Don't forget that there is still an extra x that we have not multiplied by, is x here. So actually our function f is going to be x times this. So let me just copy this, right? I'll copy this expression. Okay. So this is going to be equal to this fraction, but this is multiplied by 1x, right? So that is our expansion, or our function, if we perform this sum here. Okay, this is one way, right? And then to proceed from here, as I said, we could just find the roots of the denominator, so factorizing this into factors, and then do an elementary fraction expansion and see if we can expand the rest and see if what we get is something of the sort that is this here. But we are going to proceed in the opposite way. Given that we know the answer, what we're going to do is to calculate the function, but not summing this as we have done so far, but summing these terms here, which is easier. So what we're going to do is the function f should also be, if this identity is true, equal to the sum from 0 to infinity of z to the n and x minus 1 over 2 to n plus 1. See, that's the first term here. And the second is equal with a plus, and it's added. So plus the sum from n0 to infinity, z to the n, and then x plus 1 over 2 to n plus 1. All right, I'm going to work with this because the result will be, for this one, will be the same with this different sign, right? So what I'm going to do here is to rewrite this expression. So let me work this out here, okay? It's going to be, there is a plus 1 here, which I can deal with by taking out the factor, right? And then the rest has this form, right? Is z multiplied by x minus 1 over 2 square everything to the power n. All right? So this is the geometric series, and the answer is therefore x minus 1 over 2 divided by 1 minus x minus 1 over 2 square z. Okay, then the f is going to be this. So let me copy it. Okay, it's going to be this. Plus the same thing. All right. But with a plus here. Okay, because we have the same thing with this different factor which contains a plus. So in other words, the function that we have obtained here has to be identical to this one. Well, is it? Well, this is something that we're going to see in a moment. So what we're going to do here is to reduce this to a common fraction. Okay? So let's make the product of the denominator, right? So we have to multiply this factor over 2 squared times z by this factor here. Okay, let me see one moment. Right. Okay, so let's do that. So 1 by 1 is 1, right? Then we have minus x minus 1 over 2 square. Let me just factor the z, right? So plus x plus 1 over 2 squared times z, right? And then we have to multiply these two factors, from which we get a z squared, of course. But now you see this factor by this factor, this is sum times the difference, so it's the difference of a square. So the factor we're going to get is x squared minus 1 divided by 4, right? 2 by 2 is 4, square, okay, because there's both factors are squared, and then by z squared. And let me just simplify the denominator, right? This factor here. So what we have is 1 minus, let's see. So I expand this binomial, so I get x squared divided by 4 minus 2x divided by 4, which is x divided by 2, plus 1 divided by 4, right? And in this case, I have the same, but with a plus. So x squared over 4 plus x half plus 1/4 times z times x squared minus 1 over 4 squared times z squared. This cancels with that, and we have twice the same thing. So this is equal to 1 minus x squared divided by 2 plus 1 divided by 2. So x squared plus 1 divided by 2 times z plus, and then we have x squared minus 1 over 4 squared z squared. All right, this is the denominator of this fraction. So when we multiply these two denominators, and you can compare with the expression that we have here, and then you see that they are equal, right? You have x squared plus 1 over 2, right? X squared plus 1 over 2, and then x squared minus 1 over 4 squared, x squared minus 1 over 4 squared. So we have the same denominator. So we have to now look at the numerator, right? And for the numerator, what we have to do is, of course, multiply this by this and this by that and add them up. Okay, so what we have is x minus 1/2 multiplied by 1 minus s plus 1 over 2 squared times z, right? Plus x plus 1 over 2 times 1 minus x minus 1 over 2 squared times z, right? This times this times this. Okay, so we need to do some calculations now. Let's see. We have first this term, well, of course this is a bracket. We have this term times 1 plus this term times 1. So what we have is x minus 1/2 plus x plus 1/2. This goes with this. We're going to have x half plus x half. So this is x. Right. Now we have minus x minus 1 over 2 multiplying x plus 1/2 squared times z, this times this, right? And then this times this is minus x plus 1 over 2 x minus 1 over 2 squared times z. All right? Well, x is x. Okay, after simplifying, we just get x. And now in these two factors, we can see that there is a common factor. The common factor is this and this. Okay? They both contain these two factors. And now the first one contains the factor x plus 1 over 2 extra, and the second one contains the x minus 1 over 2 extra, right? And then both contains c, right? This and this are equal, so this is x. So what we have is just x, which is a common factor of 1 minus this, but you can see here is the difference times the sum, so it's x squared minus 1 over 2 times z. And if you compare this with the numerator of the f, you can see they are both the same. Sorry, by the way, this is 4, it's not 2, because it's 2 by 2, so 4, right? So it's, you see, it's identical to the, let me just copy this expression down here to compare, to make the comparison easier, right? Probably would have taken less time just copying it, but anyway, to avoid any confusion, so here it is. Okay, this is the final expression for f, and you can compare now the numerator here, all right, and the denominator here, and they're both the same. So the identity is true.